Hi, this video is to complete section 4.7. We are trying to optimize functions, and we began a lot of this in class. So I'm looking at these notes, and I want to remind you of the process is you often find a derivative, and you're locating what you're trying to minimize or maximize within the problem. And you write that down, and then you choose a constraint function that relates the variables involved. Sometimes you'll need to draw a picture. So with that said, let's go through our notes. We have done these problems that we did in class, and so we won't be doing those, but they're in your handout, and here they are. Pause the video if you missed class. I'm going to flip back over, and we're going to look at this problem first, okay? So I am making this with my phone, so if it becomes a little sideways, it's because I'm trying to keep things done. So bear with me. We're going to begin with the problem about the swimmer, okay? So you have a swimmer is 2 miles in the ocean and wishes to get to a town 3 miles down the coast, which is very rocky. The swimmer needs to swim to the shore and then walk along the shore. He can swim at 2 miles an hour and walk 4 miles an hour. To what point should he swim along the shoreline so that the time that it takes will be to a minimum? So we are trying to minimize time in this problem. So remember, the first thing you do is decide what you're maximizing or minimizing. So we are trying to figure out time. So the swimmer is here out in the water. Okay, he's right in here. And this is the rocky shoreline. And he's going to swim either here and then go, or swim farther down, and that's what we're trying to decide. So with that said, we need some variables, and so we're going to need to find this piece, which will be how far he swims, and then this other length is going to be different, but he's going to swim this distance. So if this is x, then this will be 3 minus x. Okay, now I'll set it up like that so that I'm dealing with just x when I work with that triangle, because we're going to have to work with that triangle. So sometimes you have to think about what would be easier. Okay, so we want to figure out his time when he swims along y and then walks along that 3 minus x length. Okay, so we're going to be using the idea that distance is equal to rate times time to come up with a time equation. So first of all, when you swim, he's going to have a swim time and he's going to have a walk time. Okay, so basically time is distance over rate, okay? And that's how we're going to come up with our equation. So we'll say we're going to minimize time. And remember, it helps if you write down what you're doing. Sometimes that gets you extra partial credit also. Okay, so minimize the time. And so when he swims, it says that he can swim at 2 miles an hour and walk at 4 miles an hour. So those are your rates, and you're actually going to be working with this formula for swimming and that same formula for walking. So you're going to say that distance he swims is y over that rate. So your time will be y over the rate of swimming 2 miles an hour. And then you're going to say when you're walking, that distance is 3 minus x. So you're going to have a time of that plus 3 minus x over the walking rate, which is 4. And this is how you come up with that equation. And so we have to minimize this function, which means that at this point, the second step is figure out how to relate the two variables x and y so that you can have one variable when you differentiate. So we're going to come back over to our triangle, and we're going to use that triangle to figure out y in terms of x. So if you use that triangle, you got x squared plus 2 squared equals y squared. So that would mean y is equal to the square root of x squared plus 4. Okay, and we're going to take that and plug it in our time function. And that's now over 2. And now we have one formula in terms of time. And this is what we will differentiate, okay? So at this point, we'll bring this power up, bring it down, take the derivative, solve it, and I'm not going to go through that process because I think the setup is what's hard here, but I'm going to show you the results so you can pause it and finish it out if you'd like. But basically, you're taking that derivative and doing all that derivative, solving this for x. You actually come out with plus or minus 2 over square root of 3. These numbers are not nice, but I show you this because you may have to set something up and not solve it. This is a calculator necessary problem. It is also on the interval from 0 to 3. Okay, so it's actually closed. So when I get those critical values and solve it, you actually come up with 1.1547. And I'm going to stop with that one. Okay, so that's the setup on that problem. Let's look at number 2. Okay, so this problem, when you set up a problem like this where you have overlapping rectangles, it is typically easier if you will try to keep your variables for the larger pieces because the terms will not become as complicated. So this is obviously about area or perimeter. So here's our problem. A farmer has 120 feet of fencing with which to enclose 2 adjacent pens shown. What dimensions should be used so that the enclosed area will be a maximum, and then what will that area be? Okay, so this is a more fair problem when you're dealing with no calculator. So first of all, you got to figure out what x and y will be. If you're looking for the maximized closed area, okay, so we're going to write that down first. Maximize area. We want to be able to write area as simply as we can. So I'm going to come over here and make this x. And instead of making the little short piece y, I'm going to make the whole length y because we're maximizing that entire area. So your area is going to be simply x times y, okay, if you'll do it this way. If you do it by letting this be y, then your terms are going to come out completely different. In the end, you should wind up with the same answer, but that's the best way to set that up. Okay, so after you've set up what you're maximizing, you have to figure out how x and y relate. So in this case, we have 3x plus 2y for the perimeter. So you're going to say 3x plus 2y equals that perimeter 120, which is the fencing. Okay, so then you're going to solve for y. And then you'll have y equals 60 minus 3 over 2x. Okay, then you're going to take this, plug it into the area, distribute, okay, and then you'll take the derivative, okay. Okay, so here's the work for that. I'm gonna let you finish by just going through the motions. I think the hard part is the setup. So after you've solved for y, you'll take that part and plug it back into the area formula. Simplify it before you take the derivative. Make sure you're labeling a and a prime clearly. When you take that derivative, you get that and you set it equals 0, you get a critical value of 20. Okay, so this is going to, if we're using from 0 to 120 as our closed interval, because that's actually what this is, 0 to 120 is a closed interval. Then we're actually evaluating at 0 and 120, and you should be showing this work for something like that, because this is showing how you're evaluating the closed interval. And so the area winds up being 600. The question asks us for the dimensions. So once you figure out the x, you can go back and plug in and get y and write your answer clearly. 20 by 30 feet and maximum area is 600 feet. Be careful with the units, okay? All right, so there's that one. We're gonna turn over now and look at the back. We got two more, okay? So let's go to the next page. All right, so here, just talking about the setup again, because here we go. A box is constructed out of two different types of metal. The metal for the top and the bottom, which are both squares, costing $1 per foot, and the metal for the sides costing $2 per square foot. Find the dimensions that minimize the cost of the box where you have a volume of 20 cubic feet. Okay, so go ahead and pause the video and try to set that up yourself if you'd like practice. Okay, we're talking about a box with a square bottom, but the sides are not necessarily square. So we're dealing with something like that. Okay, it's not a perfect box, but the bottom is a square. Okay, so the bottom's gonna be x by x, and the height's gonna be y. Okay, and so now you need to figure out the two different things described and their cost. Okay, so the top and the bottom is going to cost you $1 per square foot. Each top and bottom is x squared in surface area. So the cost is equal to $2. I'm sorry, there's two squares, but it's $1 per square. Okay, so it's 2 times x squared. That's the area of the top and the bottom added up, times the price, which is 1. Okay, so that's your cost. And now we'll talk about the sides. The sides cost $2 per square foot. So this, again, be clear, top and bottom, label. Okay, now the sides cost $2 per square foot, and you have 4 sides, so the cost for the sides is 4 sides with areas of x times y times $2 per square foot. Okay, so there's your equation, and you're going to wind up with 8xy for the cost of the sides. So the total cost is going to be 2x squared plus 8xy, okay? And now we have an equation representing cost. Then you want to see if you can relate x to y somehow so that you can plug something in. Okay, so in the problem, we were also given volume. So volume is going to be the other equations that we use. So we're going to go over and write an equation for volume and say the volume is 20. Well, the volume here would be length times width times height. So x times y. So x squared y is your volume. And that is equal to 20. And if I want to take this and plug in for the y, we can get it all in terms of x. Now you might be thinking, well, why don't I use x squared because it's here, but make sure that you can clear out without creating more problems. If I plugged in 20 over y for x squared, I'd still have two variables. So it's easier to plug in for y because there's only one y in the cost function. So y is equal to 20 over x squared. We'll come over and now we're going to have our cost function in terms of just x. And we're going to simplify our cost function. 160x to the negative 1. I'll go ahead and write it like that since I'm going to differentiate it next. Okay, and then the next thing that I'm going to do, and this one gets kind of big and ugly. I'm going to just show you the work because the video is getting rather long. Okay, you're going to set it equal to 0. Okay, and you're going to, after you take the derivative, obviously, find those critical values. Okay, so here, this is actually an open interval because we do not know the exact end of what we're dealing with. Okay, so if you need to go through all of that, you can. The numbers here come out kind of ugly. Okay, so I don't think you'll have anything that difficult on a test, but you may within your assignment. And because it's open, we're actually doing this type of calculus to show that it's minimized. So you're trying to show this wherever you can. Remember to label C prime. You actually get down to 2 times 5 to the 1/3. You can see over here we're actually factored it. Okay, and then your answer is not nice, but it is that. Okay, and so one more example, turning over. We're going to talk about this one. And so we'll talk about how to set this one up. Example 3, find the dimensions of a 12-ounce can constructed with the least amount of metal. 12 ounces, 355 milliliters, which is cubic centimeters, 355. Okay, so here we go. Volume is given, surface area is given. We want the dimensions of a constructed can, which mean that we're dealing with a surface area being put together. So we're actually getting the least amount of metal, which is the metal is about the surface area. So we're actually going to minimize surface area. Okay, and we'll use this formula. Okay, so with that said, this formula actually has R and H as variables. So we're going to use this other formula, volume, to write it in terms of just R, because we have the volume, and the volume is 355. Okay, so what you're going to do is take the volume formula, okay, take the volume. So my formula that I'm minimizing is 2 pi R H plus 2 pi R squared. And it has 2 R's in it, so we're going to plug in for H using the volume. Okay, so let's go on over here, and we know that the volume is given to be 355, and that is equal to pi R squared H. Okay, solving for H in terms of R, I come up with that, and I'm going to take this and plug it in for H in the surface area formula. And now I have an equation that's in terms of just R. Now, it is not beautiful. So if I simplify this, I could come out with r to the -1, the pi's could cancel. I'm going to actually have 710 r to the -1 if I simplify, plus 2 pi r squared. Okay, and that's what I'm going to take the derivative of. And I'll get -710 r to the -2 plus 4 pi r. I'm going to set that equal to 0. Keep in mind here that r cannot be equal to 0 for my answer. It would be a critical number, but we're doing that open interval thing anyway. So we're thinking about the surface area, so we can't have negatives. And then I'm going to keep going and simplify this. This does not come out to be very nice, but I'll show you what I do have on this. And so you can use that to kind of estimate how you deal with some of these rational exponents. And so that is some examples of things you could run into in your assignments. And I think you've got quite a few examples to ponder. So work hard on this. And if you get stuck on one, just move on to the next one. Remember that some of these can be very challenging. Remember, it's okay to keep going back. Okay, so happy mathing.